time to start. So, welcome everyone to this course in embedded control systems. And this is basically the last course that is fully compulsory in the program before you start with the design project and the master thesis. So, the main idea behind this course is that you will now have a chance here to practice what you learned in the previous courses. So you took in the compulsory part, you took the discrete event systems course, you took the modeling and simulation and linear control system design course. So all those courses, they built up your toolbox with different methods that you can use. And now you will try to put that into practice. So this course has over the years evolved more and more into a project course. And what you will do this year, it's the same project as we did last year. You will have you will be divided into groups of 4 students, and each group will get a quadrocopter. It's a really small one, but it's good because it's also safe, so no one will be harmed. That's something you think about when you have some form of responsibility. So. Yeah, so the whole course will evolve around this project. So we will have lectures. In total, we will have 14 lectures, and most of them will talk about things that you will later on work on in the project. So the course organization is like this. So we will have these 14 lectures I talked about. And then you will be divided into these groups of 4 students in every group, where we work tightly together on this project. And we try to meet once every week, but unfortunately it was a little bit many of the different Thursdays and Fridays when we have these meetings are not available because of holidays this quarter. So we were only able to squeeze in 5 of these weekly meetings. But there you will meet with a teaching assistant. So you will have 1 hour together with the teaching assistant on every of these occasions. And you will be 3 groups in total that meet the teaching assistant in this 1 hour. And for every of these weeks, you will have assignments that you need to work on. And there are tasks specified that you should present at these meetings and to discuss if you have any problems. But of course, so there is a significant amount of work to prepare for these meetings. So I will come back to that, because that also means that you have to think about how you form these groups as well. So we will recommend you to form groups where you are all in the same, taking another course that is in the same block, so you can meet each other. So in this course, we also have a part on ethics included. So ethics is something that should be included in every master program, and we have to squeeze it into one of the existing courses. So that's one part. We will have a philosopher to come here and to discuss about ethical issues, and then you will have different cases that you have to think about and to learn how to reason about ethical problems. And you will also write a report on this that you need to hand in. And we did change how we taught this last year, and I think we now have a structure that works really well, actually. So although there is always, so this is not really part of the course, but it's part of the program, if you understand what I'm saying. So, but it is, so when you start to work as engineers, I can guarantee you that you will run into ethical problems. And then it can be really good to have these sort of framework. How can we reason about, how can we identify the different stakeholders? And how can we in some systematic way arrive to a way to how to act in a specific situation. And we have a lot of deadlines especially for these project meetings. So, but if you log into Ping Pong, I'll bring it up here. I've tried to make it convenient for you, so you can here I have structured every week, so you can see what to do when you have deadlines. So the first project meeting will not be due to that it's Easter, will not be until study week 3. But as I say, the first project description is already out, so I really recommend you to start work on this project as soon as possible. You will, on Thursday, we have the handout of the crazy flies. So there will also be an introduction on how to work with the environment, how to program the crazy fly, and you will work with MATLAB and Simulink and Simscaping. We do code generation, and you will also write the C code yourself. So on Thursday we would like you to have formed the different groups, and if you have not yet found a group or been able to form groups that fulfill the constraints, I will soon talk about that. Yeah, just show up here and we will put you into a group. What else? So in addition to the meetings we have, we also have different consultation hours scheduled. So if you can, try to show up at these meetings, because then the TAs are prepared to answer your questions. So then in the end, there will also be, you will present the projects, the final result of what you have done. So hopefully this quadrocopter will fly that time, and it will be stable and nice. So this will be in May. And there is, so it's compulsory attendance for these groups as well. And you will also have to hand in a final project report on these things. And then the last day in May is there's an exam as well. What else? Yeah, so I didn't print out the course syllabus, but the course syllabus is here. You can find out, there should be all the information you need, I hope, regarding what is allowed to bring to the exam. I did a change this year, so it will be allowed to bring one A4 sheet with handwritten notes on both sides. To decide yourself what to put on that note. You will also be allowed to bring a technical report that I will also print out for you called Essential C. So, because there can be programming assignments, but since you have a quite different background in C, some of you have never seen it and some of you have worked a little bit more with it, you're allowed to bring this technical report that can help you with that, to get the syntax right and so forth. So we see, go back to the, So since the project is such an important part of this course, it is important that everyone that will follow this course have fulfill the prerequisites. So if you're an MPC student, that's not the problem. But you come from some other program, you are welcome, under the assumption that you have taken these two courses. Otherwise, you should take another course. We have tried to have students that have not taken these courses before with not so good result. Because what happens is that it's too complicated. You will not be able to contribute to the project. And the discrete event systems is good to have, but it's not strictly necessary. You can pick it up what you need. Any questions about this? So I hope this should also have been clear from the student portal in case. If you haven't noticed yet. Okay, so what are the learning outcomes in this course? So basically what we try to do now is to go through all the steps that you need to do when you design a controller for a real system. And we try to do it in a model-based way. So meaning that we have this physical system, and we will build a model that we can simulate of this system first. So given this model, it will be a non-linear model. And then you have to linearize it to get the linear model, and then you will apply the knowledge you gain from the linear control system design course. So you will design an LQ controller for this for rotor, and then you will do two different things. You will generate the code from these tools. So we will use Simulink and the embedded controller toolbox that will generate the C code for you automatically. So you can quickly get started and see some results. But when you have done that, so at the end of the course, we will also talk about what's going on under the hood. So we will talk about the microprocessor, how to program a microprocessor using the C programming language. And we will talk about real-time operating systems, because this tiny quadrotor has a 32-bit processor, and it's running a real-time operating system called FreeRTOS. So, and in FreeRTOS you can have multiple different tasks running in parallel. So we will learn about how these things work, how to build up basically a scheduler, and how the scheduler will then decide which task to run, because only one task can run at a time, so the different tasks, they share the same processor. So we will learn about those things. So semaphores, for example, to synchronize different threads. We will learn about different scheduling techniques. We can analyze this, rate monotonic and earliest deadline first. And some problems that show up that are real problems that changes or can have effects on the control behavior. And then towards the end of the course, we will also talk about how we can formally write specifications for these systems. So I think this year Bengt introduced temporal logic in the discrete event systems course, at the end at least, a little bit. So now we will actually start to use temporal logic. So we will formally describe or set up properties that the closed loop system should fulfill. And then we'll use an extension of linear temporal logic called signal temporal logic. So we can start not only to reason about Boolean variables, but we can also reason about analog values and timing of different values. And then we'll talk a little bit about a project we are working on together with Volvo Cars, where we're doing test case generation from these signal temporal logic based specifications. So with the idea to automatically be able to generate test cases that can falsify the requirement if it's possible. So you know that, for example, in a car it's an extremely complex system, so there are hundreds of millions lines of code, and they interact with the different components. They interact in a lot of strange ways. So it's extremely important now to have software that has as few bugs as possible, that you are able to sort of systemize how you test these systems. So this is a very hot area in industry right now, and we will basically touch upon what we're doing in the research projects right now. So we do everything from modeling, control design, implementation, and then specification, testing, and verification as well. So sort of we try to bring everything together in this course, which of course is a challenge both for the course and for you, because there are many different aspects that we will talk about here that comes up. So, and that's a challenge also for us teachers here to know about the details in all of these different fields. And on top of this, we also have the ethics to worry about. But for that we bring in this philosopher to help us out with that. So, I talked about model-based development. So what is really model-based development? Yeah, so as you can hear from the name, you use the models. You build up the models. And typically what you try to do is that you, on the models that you have built up, so you build up not only a model of the software, the controller, but you build up a model of the controller and the environment, the physical environment that the machine is interacting with. And typically you have the specifications on the closed loop system. So the machine interacting with the environment. So you need to consider how they interact with each other to decide if the specifications are fulfilled or not. And then of course you do a rough design. You start to decide, okay, which control structure will I use? What kind of hardware will I use to implement this? Will I have multiple microcontrollers, or will I try to save some money and one microcontroller and then put multiple control tasks on the same microcontroller or not? So this is something that I know they are working on in the automotive industry now. I think in the latest SSY190 there is about 120 different microcontrollers running. And of course they would like to reduce that, because then you can simplify the architecture, and you can of course also potentially save some money with that. So after you have decided on your control structure and your hardware structure, you go on and then design the different control algorithms and try to tune them so they behave in a nice way. And of course, if you have built really good models, then you try to evaluate as much as possible on your simulation model. So that is something you typically call model-in-the-loop testing. And you would like to do testing as much as possible on your models, because the models, they can scale. You can buy a huge cloud server, so you can have thousands of different processors running in parallel. So there you can really test a lot of things. But as soon as you start to include hardware in your testing, of course at some point you need to do that, but hardware doesn't really scale very well. So it's much more expensive to try to find errors if hardware is involved. So the better models you can build, the better you can trust your testing that you have done on your models as well. So that's another benefit from having models. I mean, you have previously designed models because for example, you would like to use the models in your control design, right? but you would also like to use the models in later stages of your development. And typically what you try to do here when in this model-based development approach is that you try to do testing at every level here. So you have defined all your small components, control algorithms, etc. Then you try to test them separately. And then, of course, then you try to combine them together and test how the interaction, if that is all right or not. And then you put that in the whole system, and then you check against your original specifications that you set up on your closed loop system. Yeah. So this way of doing the design and the testing is called the B models. You've probably heard about it before. Okay, so with this, I'm just trying to say that we try to go through all these different steps in this course the best way we can. So what is a bit interesting, though, is that there are, at least to my best knowledge, no other course that really tries to do the same thing that we are doing. So there are courses on, for example, the implementation aspects, real-time systems courses, typically given by the computer science department, where you learn about real-time operating systems and scheduling and all that, but they don't learn about control algorithms and the interaction between the schedulers and the control algorithms. And then, as you have taken other control courses, but they are typically, they focus on ideal situations, and they don't worry about the implementation aspects, but the implementation aspects also matters. And I think it makes a lot of sense to have such a course in the master program to try to do everything. But there are no really, to my best knowledge, available literature that describes how to do this whole process. So we will. So the main course literature will be the lectures that I use. And the lectures are then based on material from various different books. And I will talk about some of them here. So there is a course book called Principle of Cyber-Physical Systems, which is a very nice book, talking about formal specification, linear temporal logic, those kind of things for cyber-physical systems. But it doesn't really talk about control algorithms, and it's not really helpful with the design of the quadricopter. So for the quadricopter, there is another book called Robotics, Vision and Control, Fundamental Algorithms in MATLAB, that is available on the Chalmers library, so you can just read it online there. That's the same thing for this book, by the way. So you don't have to buy any book at all in this course. Just go and read them when you need to. And we will also already today start to talk about rotation matrices, because this is important for the quadrocopter. And for those of you that took the modeling and control of the mechatronic systems course, I think you use this book, Robotics, Modeling, Planning and Control. Right? So so this will be a repetition for those of you that took that course, and it will be maybe new for others. And then we will have the essential C for how to program in C. And we will talk about real-time operating systems and scheduling techniques. And then there is another really nice book available online called Operating Systems, 3 Easy Pieces, that you can go and read if you need more background than what I'm able to bring up in the lectures. Yeah, I already started to talk about the project. So the whole idea behind this project is to do the modeling, simulation, control design, implementation, and validation. Go through all these different steps. And what you will do in the end is that you should have built the dynamic model of the quadrotor in Simscape. I think most of you have not worked in Simscape. You have worked in Simulink. And Simulink is a causal modeling language. So you have to know what are the inputs, what are the outputs. But in this course we will do one more thing. We will learn about acausal modeling. And another way to think about it is that you write down the equations only, and then you model at a higher abstraction level, and then you let so you write down the equations exactly as they are in the textbook, and then you let the simulation engine solve the equations for you, so you don't have to figure out what are the inputs and what are the outputs. You leave that to the tool. And Simscape is the MATLAB version of these techniques. There is actually another very famous and standardized language called Modelica, which was created by a Swedish control guy that has implementations in various different tools. And basically you can say that Simscape is the MATLAB or Modelica. It's a Modelica dialect in the MATLAB language of these ideas. But the ideas in Simscape and Modelica are the same. Okay, so you will build this model, and then you will get a nonlinear model, and then you need to linearize it, and you will get, and based on that, do a LQ control design for controlling the roll and pitch of the quadrotor. And then you will use the model in the loop to evaluate the control design. You will simulate the closed loop system in your computer. And you will generate the C code by using tools in Simulink and deploy on the CrazyFly. So you will generate C code, and then you will use a compiler to the CrazyFly to compile the C code to a binary that you can then download to the CrazyFly. And of course, to pass, you need to have a decent able for the roll and pitch control. You should also be able to send set point signals of the thrust and roll and pitch from a smartphone. So there is, of course, an app that you can download and use for these purposes. But when you, roughly halfway through the course, you will get something that can fly, hopefully. And then what you need to do is we will look into what's going on under the hood here. To look into the real-time operating systems, and you will also learn how to write the controller algorithms yourself by using only C. So I think there is of course you do more and more code generation automatically from these high-level tools. It's much faster and better in most respects. But I think it's good, at least from a pedagogical point of view, to have actually implemented the code once. So you know what's going on under the hood here, if something goes wrong. And we will also look into some specific problems that you can have when you have multiple tasks running on the same real-time operating system. And you will write a project report about this, so there will be a draft report that will be, I think it's due in April, and you will review each other's reports, and then there's a final report that you hand in after the final presentation. So that's about what you will do in the project. But as I mentioned, you will work in project groups. And at least initially, we will have one CrazyFly for every group. So you will get a new one, and we have some old ones as well. So we might be able to borrow used ones if you think you need more than one quadricopter. But what is important now is that you, for Thursday, you should start to form these different groups. And as I already mentioned, so here you will, when working with this, you will have problems. You will have problems with the mechanical things. You will have problems with software, Simulink, C programming. Many different problems. I'm quite sure. So what we really recommend, or actually require it, is that you form groups now where you have a broad experience. So we don't want only said students to work together, because you will not really have the competence to work to solve this alone. So instead we would like to have groups where you have a mixed background. And we would also like you to form not only Swedish groups or international groups, we would like them to be mixed. So, if you're forming a group on your own, you have to fulfill all these 5 constraints. So, the first constraint is that each group is required to have at least one student that did not study bachelor program at Chalmers. So basically an international student. And each group is allowed to have at most 2 students that did not study a bachelor program at Chalmers. So we need to have Swedish students in every project group as well. And each group is required to have at least one student that did study a bachelor program at Chalmers. And on top of this, we would like to, or we require you to have at most 2 students from the same bachelor program. And then you should have 4 members in total. So, if you can form a group on your own that fulfills this criteria, you can now log into Ping Pong and join a group. So we see here. So I think if you go here, so go to the project groups, and then all the constraints are written here. Yeah, and now I should mention that since it's a considerable amount of work in these projects, we know from previous years that it has been a problem if you take the other course and yours that is scheduled in different blocks. So as long as it is possible, we recommend you to form groups where you are taking courses in the same block. And I know that many of you are now taking the Sensor Fusion course. So for example, so we take that in particular, where there is also a lot of project work. I think it's really good to work together. Yeah, and then you basically assign into a group, so each group has a different number. And here you find how different group numbers are then organized into blocks. And you will meet your supervisor, or the coach, we can say, the teaching assistant, in these different blocks. And if you know that you need to have other activities, so for example, if you log in here, you can see that all the project meetings, and maybe you know that, okay, this is a good time for me to meet the supervisor, so Fridays so we have basically 2 slots, Thursdays from 10 to 12 and Fridays from 3 to 5. So if you have any preference here, then join a group where you have a block, so block G for example. Would like to attend that. that means that you should join group 19, 20, or 21. So, this way you can also influence when you will meet your supervisor. Yes?
Is any of these combined with the sensor non-linear filtering course, sensor fusion course?
I hope not. We should be in different. We keep to the block that we are assigned to. So.
Because then these blocks are not meeting like that. So if there will be no collision.
I hope not. But there are, of course, depending on what other courses you take. I mean, it's up to you to take courses that are not in the same block as this course. Okay. Yeah. And then for the final presentations, we mix the presentations from different blocks here. So, is this clear? So just in ping pong, you log in and join a specific group. And if you are not able to form a group, show up, or you're supposed to show up on Thursday anyway, but then we will put you into different groups. What is also very important is that every project member should then attend every project meeting. You are allowed to miss one. We will, because people get sick and so on. But you can't systematically not showing up at the project meetings. Then we will arrange something special for you. What is also important is that every project member should be able to answer every question from the teaching assistant that you meet with. So every project member should be active in all parts of the project. So it's not okay to divide the work between the different project members. This is important. Yeah, we already talked about exams May 31st, and that you can bring this one A4 sheet and have written notes. And so how does the grading work? Basically you can earn in total up to 30 points. And the written exam is for 23 points. And to pass the exam, you need to have at least 10 points at the written exam. And on top of that, you can earn 5 points for the project. You need at least 1 point to pass the project. So, but if you didn't do well, you will get 1 point. Or, I mean, if you don't do, if it's too bad, you will fail the project and then you will fail the course. But I hope that will not be the case for anyone here. So it should not happen if you just work on the project. But you can get up to 5 points for the final. That will be added on top of your written exam. On top of that, you will also get, or might get, up to 2 points on the ethics essay that you write. And we should mention that all these are individual. Actually, all 3 of them are individual. So it might very well be that you get fewer points than what other group members do if you're not contributing to the project to full extent. Yes? Yeah?
Are we supposed to write individual reports for the project?
No, you're not. You're writing one report for the whole group. But in the end, you will also So the teaching assistant, they will meet with you and they will ask you. So we will keep an eye on you. So we'll see that everyone can answer questions. And if we identify problems, we will first arrange a special meeting, but eventually it might end up that you will lose points. And you will also, in the end, you will file an individual report about how the group work has been working out for you. So there you will also give comments about everyone else in the group, how much they contributed and so on. Okay, but we hope, of course, that everyone, this should not be a problem if you just work and show up to the meetings and contribute. So, in most cases, every member will have the same point, we believe. Yeah, and we also have some course representatives. I don't know if you recognize yourself here. So we will try to have a midterm meeting, and then there will be a final course evaluation meeting in September, I believe, unfortunately. But, so if you have comments about the course, so contact them, and or you can of course contact me directly if you have comments. But you can also go through these. Yeah. So about your responsibilities. So as I said, every member in the project group should take fully part in every aspect of the project and be ready to answer any question. And it's everyone's responsibility to make sure that this happens. So in case you have a group member that does not really contribute and follow the project group, you should contact first the teaching assistant that you meet with and discuss, so we can try to solve the problem as early as possible. So, and if you don't contribute, you risk failing the project, and then you will fail the course as well. And you can't do the project until next year. So it's not a good idea. And we have this individual group evaluation that I just talked about. And you can get different number of points on the project as well. You will also write a report, and it's important that you write the report on your own, so you don't copy what others have written. So in worst case you can be suspended from Chalmers, but once again, don't do it. There are documents for what that specify what is allowed and what can happen. That are linked from the homepage. Can read. Yeah. So these, well, in case you get sick, contact the examiner for the final project presentation. So all the group members should be there as well. And then we will have this guest lecturer, the philosopher. So of course, when we have guest lecturers, then I would like everyone to be here. So I have decided to have compulsory attendance on that day. Otherwise, the lectures are, of course, free to attend. But I think it can be helpful anyway. I hope. So what to do today? You should form project groups. You can also go and start to look at the first project. And what you really need to do when you get the quadricopter on Thursday is to make sure that you can run the software that you need to run. And what you will do is that you will have a virtual Linux computer that you will run on your own computer, and you will use a tool called VirtualBox to do this. And it's really convenient to use because you get everything set up for free. Basically, so you have everything, the cross compilers and the tools to watch the sensor values and so from the quadrocopter, you will use a radio model to communicate between the trade supply and your laptop. And this Linux computer is identical for everyone. So in case you have a problem, if you mess up, you can all just download a new trade supply virtual machine and continue to run. And you will also use MATLAB. So install a recent version. I think 2016B would work as well, but yeah, just this is what we have tested with. So Simulink, Simscape, embedded coder should be installed. Then you will be fine. So those things you can work on today. Yeah. So with that, we will start to the lectures after the break.